thing I'm showing you, you do not have a handout for. So it's just something to remind you of what we introduced last class period, is that there's two different ways to show if something is polar. For example, on your quiz today, we might ask you to show polarity at some point. The two ways to do that is either these partial symbols, partial negative and a partial positive. What I state right next to the partial negative is this is the end of the molecule that's more electronegative, so it has a greater share of the bonded electrons. So recall that this line between the H and the O is 2 electrons being shared. However, oxygen has a greater attraction towards the electrons than hydrogen does. So even though we draw a line here, it's a little more realistic to think of the electrons closer to the oxygen than the hydrogen. The hydrogen still has a hold on it, but not much of one. That's why it's the partial negative end. The negative electrons are closer to this side than they are here. The dipole moment arrow is once again pointing in the direction of whatever element is more electronegative. Because once again, there's a greater region of electron density, which you might get a better understanding of when I show you a little computer simulation here in a little bit. But that means again that this is a polar covalent bond, and therefore a polar covalent molecule. What we're going to work on right now is a handout you picked up on the way in titled Computer Program on Polarity, and then it says Homework FET. This isn't going to be homework, it's something we're going to do right now, and I'm curious if this thing is going to be around much longer because it runs off of Java. So it start with the 2-atom page. Yep, we did that. On the right side of the page, be sure to check bond dipole, partial charges, and bond character. Here's bond dipole, partial charges, bond character. In the second box, make sure to check electron density. And the electric field should be on. Notice how I have a positive plate and a negative plate here. Number 2 says at the top of the screen is a gauge for electronegativity for both atoms. Set A to the lowest electronegativity and B to the highest. A and B are meant to be generic elements. They could be any element. So don't get thrown off by why is that a letter A and why that's a letter B. It's variables, if you will, from a mathematical sense. What I'm trying to show you here is if A has a low electronegativity and B has a high electronegativity, bless you, notice how it's darker near the B. The bottom says this is a high region of electron density, therefore. Notice that there's a dipole moment arrow pointing in the direction of whatever element is more electronegative. Lastly, notice, and it might be hard to tell, that next to B there's a partial negative sign, and next to A there's a partial positive sign. Number 3 says what atom has the partial negative charge? You can fill that in right now for number 3. What atom has a partial positive charge? You can add that in for number 3. While you're doing that, I'm going to do number 4. Use your cursor to try to rotate the molecule. So I can actually grab this and spin it around however I want to. However, one of the pieces of evidence that we have to support the claim of polarity is, notice right now how I'm holding it. I have the partial negative B next to that negative plate on the left-hand side. If I let go, nope, it always returns because opposite charges attract. Again, we know of polar molecules because of an electro or a magnetic field that it's going to respond to that. Again, I can spin this thing around, let go. It's always going to return to have that the case. So in number 7, it says, in a complete sentence, explain why the molecule rotates back to the starting position. 2 things we have to remember. One is that opposite charges attract. Again, that I've been talking about for a good portion of the year. Secondly, polar covalent molecules have a charge. It might not be a full charge like ionic, partial, but it is still some sort of charge. And as I said last time, ladies and gentlemen, polarity is a big topic for us. Our entire next unit is talking about how polarity plays a role in state of matter for things, how some things are able to mix with other things, and sometimes not mix. It all has to do with this topic. As you're finishing up number 7, number 8 says set your electronegativity value to the lowest for A and the highest for B. I already did that. Which one has the greatest electron density? Well, you notice that B is more electron dense. Recall from first unit, density is just how much stuff you have in a general space. When B has a higher electronegativity than A, that means the electrons are closer to this side. That means there's more electrons in this space than in that space. Okay, that's what the dipole moment arrow is trying to represent. And again, that leads us into number 10 of in a complete sentence explain why B has a partial negative charge. Remember, in any covalent bond, there's a sharing of electrons. However, is it equal sharing or not? That's what we have to be able to recognize. As you're finishing number 10, number 11 says keep atom A at the lowest level and move the setting for B up to the highest and then back down to the lowest. As you do, watch what happens to the arrow above the two atoms. So if element B was not really electronegative, notice that the arrow is getting smaller, and then it's gone. Hey, when that dipole moment arrow disappears, what type of bond now exists between A and B? Non-polar covalence, because it's an equal sharing. Quite frankly, if I started rotating this and letting go, it doesn't care. Because non-polar has no sort of charge at all. But if there is at least a little bit of difference, it can now be polar. Again, number 12 says put the setting for B in the lowest possible, move A. So it doesn't matter which one is high electronegativity or low electronegativity. If there's a difference in electronegativity, there is a slight dipole. I even like this animation because, boy, I don't know if you can see that up front, Summers, but there's tiny little partial positive and negative symbols there. Max, I'm guessing you towards the back cannot see that tiny little partial positive and negative sign.
And I can see, like...
There's something there?
Yeah.
But if it was a doctor's eye chart, you wouldn't be able to say what it was. But as I increase the electronegativity of A, there's a greater and greater unequal sharing of electrons where it becomes more and more polar. One of the tricky things about polarity is it's not a black and white thing of you're polar or you're non-polar. Because if there is even a little difference, it is slightly polar. However, notice how slow that is to respond to the magnetic field. Instead, I cranked it. It's going to switch over right away. So the front page of this was trying to show you the difference in electronegativity between the two bonded atoms. And again, we just use variables A and B. And how to represent that. Like this dipole moment arrow. Partial charges as well. If you flip to the back side, question 13 says, in a complete sentence, explain what the arrow represents. And then hint in which direction does the arrow always point to. Why don't you take a minute to answer number 13 on the back side of this sheet. As you're finishing up question 13, number 14 says put the electronegativity setting for A and B to the maximum amount. Is this polar covalent or non-polar covalent? What do we say? Non-polar. Again, two things with high electronegativity will share electrons equally. Common mistake that students make is as long as one thing has a high electronegativity, they assume it's polar no matter what. That's not always the case. Notice that there is no dipole moment arrow. There is no partial charge set here to represent that. And as you finish up 14, number 15 says, put the setting at the minimum for A and the maximum for B. What type of bonding is this now? Polar covalent or non-polar covalent? Polar. There's an unequal sharing of electrons. So for number 16, I have selected methane, which is CH4. Again, if I get rid of some of these things, maybe you can see it a little bit better. Here's carbon. Here's 4 different hydrogens bonded to it. Now, if I click on molecular dipole, notice there is no real arrow anywhere. If I click on electron density, kind of looks the same all the way around, doesn't it? If there is no dipole moment, and there is no one area more electron dense than the other, and this is question 17 on your page then, is this molecule non-polar covalent or polar covalent? What do we think? Is CH4 polar or non-polar? Non-polar. Carbon-hydrogen bonds are non-polar. There's a slight difference in their electronegativity, but not much. So we consider that to be non-polar. Number 18 says pick CH2O. Formaldehyde. Here, and let's take off the electron density first. Carbon, 2 hydrogens, and an oxygen. Hey, notice it's double bonded. This is actually one of the problems I wrote up on the board last time for you guys to figure out if you got done with Lewis dot early. Here is a dipole moment in this particular direction, because carbon and oxygen are not next to each other in the periodic table. They do not share electrons equally. Oxygen, being more electronegative, has a greater share of those electrons, which is demonstrated by darker electron density here versus this end of the molecule. And there's one last problem to do. For number 19, it says choose NH3. So again, I'll get rid of all the other labels here for a second. NH3 is ammonia. Here's a nitrogen and 3 hydrogens. Molecular dipole? You bet it does. It's in the direction of the nitrogen. Electron density? Definitely darker up here than down here. I mean, we could add partial charges if you want to. It's just that the partial charges start to give a unit called a debye, and that's beyond what we ever have to know. So that's why I don't like the partial charge label on there. So the hope of showing you this is to give you examples of how either the partial charge symbol that's shown I think pretty well with the 2 atoms example, or the dipole moment can be used to label if it is polar or not. Because again, there's plenty of things that are not polar. Diatomics are not polar, for example. So there are things though that are polar, like HF is very polar, for example. So I wanted you to see that and to be aware of that as well.